Okay. Hello. Okay. Good afternoon. So before the afternoon session, let us just mention the location of the post-session this afternoon. So it's basically in the house 3, which is the greenhouse that's next to this building, on the top floor, 6, and that's the code 4504. Is the reception? Yeah, in the same place, the poster session. Yeah. That code works for the whole floor. Okay. And let's begin the afternoon session. Today we are very happy to have Po-Shen Hsin here to tell us about the story of anomalies of non-invertible symmetry.
Oh, hello. Okay. So thanks for the introduction and invitation to speak here. So today I'm going to talk about anomalies of non-invertible symmetry. This talk will be somewhat similar to Francesco's talk in the morning, but the definition of anomalies will be slightly different. So in my talk, what I call anomalies is whether a symmetry can be realized in a trivial phase. So that's what I mean by anomalies. So because lots of people already introduced what a symmetry is, so I'll just be very brief. So what is a symmetry? Well, symmetry is conserved charge of quantum system. I think there's some noise. And conservation, hello? Okay. And conservation law means that symmetry operators is topological, so you can deform the symmetry generator from a time 1 to another time 2, while preserve the total charge. So symmetry can be regarded as topological operators or topological defects. So in my talk, I'm going to use the word operators and defects interchangeably. Okay, so what structure does a symmetry have? Well, first of all, there's fusion rule. There's invertible versus non-invertible fusion rule. So invertible fusion rule, we fuse like A with B, produce a unique answer, which is C. For non-invertible fusion rule, if you fuse A with B, you can typically produce a collection of operators, which are ideal by CI. Another data is the correlation functions of symmetry defects or symmetry operators, such as their braiding. For instance, there are braidings between 3 surface operators in 3 plus 1 dimension called the 3-loop braiding, where this loop alpha, well, let me use the pointer. Okay, where we can regard the surface operator as like a worship of some loop excitations. And if the loop alpha and loop beta are threaded by a common loop gamma, you can try to break them by like bringing loop alpha, like shrink it and pass through loop beta, and then expand it and going around to be the original configuration. So that's 3-loop braiding. And also non-associativity. For instance, if you fuse the symmetry defects in different ways, like in this picture, you can fuse these 3 lines in this way, like first fusing the first two lines, or first fusing the second 2 lines. In general, it can produce different outcomes. And let's say non-associativity. And also the fusion can be non-commutative, namely if you fuse A with B can be different from fusing B with A. Let's see, rows. Okay. So I think probably many people already know, but let me just introduce far examples of non-invertible symmetries and why are they important. So a sort of standard example with non-invertible symmetry is the 1 plus 1D Hsin model with magnet. So there are like spins that can point up or point down, and there's a Z2 spin flipping symmetry. And in addition, the theory has a so-called Kramers-Wanian duality. It exchanges a single spin at each side with a domain wall, where you're flipping all the spins on the right of the domain wall. So it's called Kramers-Wanian duality. Now, this Kramers-Wanian duality is a symmetry in the critical Hsin model, and this fusion rule does not have an inverse. So if you fuse this D with itself, it produces the identity. But in addition, you also produce another operator where you flip all the spins. So the fusion rule is non-invertible. Now, the reason such non-invertible symmetries are important because they are common in many quantum systems. For instance, they can be present in standard model-like theories in 3+1 dimension, or many lattice gauge theory models, or like Maxwell theory or some supersymmetry Yang-Mills theory. They are all over the places. So if they are there, we should study them. And for instance, in 3+1 dimension, which is the case I'm going to focus on this talk, there can be a similar non-invertible symmetry to the Kromer-Swannian duality defect, where you fuse the defect, the defect is supported on a domain wall, and you fuse the defect with its orientation reversal, which I denote by a bar here. It can produce a collection, it can produce a sum of surfaces, which I call eta. So eta is supported by supporting on any closed surfaces on the domain wall. So that's an example of non-invertible fusion rule. And such non-invertible symmetries can present in many 4D examples. Okay, so in this talk, I'm going to ask the question: what can symmetry tell us about the dynamics of the quantum system? And in this talk, I'm going to focus on unbroken symmetry. So I'm not going to talk about first law of phase transition. The symmetry I'm talking about will be like unbroken. Okay. So what are the possible phases? Well, so first of all, there is symmetric gap-based phases. You can have like critical system, like Lagrange liquid, or like CFTs, where that has the symmetry, where the symmetry is not broken. You can also have situation where the theory is not gapless, so it has finite correlation length. So it's a gap phase, but it preserves the symmetry. So such phases are important in like total quantum computation, fractional quantum Hall A-flagging. It can have like long-range topological entanglement. And a subset of such phase has trivial dynamics, so it's just completely trivial. And also it has trivial dynamics, they are still important. For instance, examples include like topological insulators or topological superconductors. They are also interesting for various physical reasons. Okay. And in this talk, I'm going to tell you how to use non-invertible symmetry to mark those boundary, reach these boundaries of those phases. Namely, suppose a quantum system have some non-invertible symmetry. Can it have symmetric gap phase? Can it have trivial dynamics? So that's the questions I'm going to ask in this talk. Okay, go to the second page. Okay, so before talking about non-invertible symmetry, let's step back to ask what happens for invertible symmetries. So for invertible symmetries, any non-trivial symmetry structure, such as non-trivial braiding, non-trivial non-associativity, implies non-trivial dynamics. And like people have studied it for like decades, like starting from Tooth, like the Tooth anomaly matching, also anomaly flow by Carlin and Harvey, and also condensed matter literature by Nayak and else. So for invertible symmetry, any non-trivial symmetry structure implies non-trivial dynamics. But the statement is not true for non-invertible symmetry. For instance, in 1+1 dimension, there's something called Z2 times Z2 Tambara-Yamagami symmetry. So it has 3 symmetry generators. One is this, as you can see that. One is this capital D. The other is this eta 1 and eta 2. So eta 1 and eta 2 generate the ordinary Z2 symmetries, the square root 2 identity. But this generator D generates a non-invertible symmetry, because if you fuse D with itself, it produces only generators of the invertible symmetry. So that's an example of non-invertible fusion rule. Now, suppose you consider such fusion rule. There are symmetries where the fusion of this D is not associative. So if you fuse this defect in different ways, it can differ by a sign. But the sign for the symmetry with this non-associativity can be realized in trivial dynamics. So that's very different from the case where we have an invertible symmetry. And in general, it's a hard problem like non-invertible symmetry implies non-trivial dynamics. So in most of the previous studies in 1+1 dimension, this can be an answer using a fiber functor, but that's very complicated. So in this talk, I'm going to give a simple solution for addressing this question, like for general non-invertible symmetries in a higher dimension or in 1+1D in any dimension. Okay. Yeah.
Sorry, just about notation because I'm
Yeah.
getting confused. So when you say trivial dynamics is like an SPT for the
SPT,
free
yeah,
category.
SPT, yeah.
And non-trivial dynamics also contains
It can be
TQFTs.
topological order, yeah.
Okay, go.
Yeah.
Okay, thanks.
Yeah. So for instance, in my, let's see, like in this slides, in a non-trivial symmetric phase that has non-trivial dynamics, there can be like logical qubits where it can do topological quantum computation. There can be fractional quantum Hall or some long-range entanglement. So the trivial dynamics has short-range entanglement. Yeah.
A bit confused about what you mean by non-associativity here. Because
yeah. What I mean by it's there's non-trivial isomorphism. There's non-trivial associator. That's all I mean. Yeah. Yeah. Okay, so I think everyone's happy. Okay, so the rule I'm going to follow is, well, basically discussed by many speakers, like in the morning and also in the previous week. So I'm going to view symmetry as like from the book TKFT point of view. So whenever a system has a symmetry, I'm going to say that I can live on the boundary of some TKFT that capture the symmetries of the system. Okay, so so the relation is that the symmetry on the boundary can be sort of as the topological defects in the book that are either ending on the boundary, or maybe you can just move the topological defect in the book like entirely like parallel to the boundary. Now within this setting, the possible dynamics with unbroken symmetry on the boundary are equivalent to asking what are the possible like symmetric boundary conditions of the bulk TKFT. So for instance, if the bulk does not have symmetric gap boundary, that means that the symmetry on the boundary implies that it must be like there must be no symmetric gap phase. And similarly, if the bulk does not have any trivial boundary, well, it means that symmetry implies the boundary must have some non-trivial dynamics. So that's the logic I'm going to use in this talk.
In by trivial boundary is this? I don't know.
Well, I'm going to classify.
You're going to classify, okay.
Right. So well,
okay,
I'm going to clarify later. You have to choose some polarization to fix the absolute theory, but I'm going to talk about it later. Yeah. Yeah. Okay. Okay. So well, let me begin by reviewing gap boundaries of bulk TKFTs. So I'm going to study the boundary of TKFTs. And this subject has been studied like for many decades, like starting from maybe Anton and like Selena and also Levin and some kind of smaller people, including like Liang Kong and Wen and others. So basically, the basic idea is that the gap boundaries of TKFTs are like Lagrangian algebra, or if the TKFTs are abelian and every operators obey abelian fusion rule, then they are Lagrangian subgroups. So there's a group multiplication structure for fusion. And the symmetric, so if you want to ask what are the symmetric gap boundaries, that means that they correspond to Lagrangian subgroups that preserve the symmetry I want to talk about. So this concept is relatively easy to study in bulk TKFTs that are abelian, because then we just need to consider Lagrangian subgroups. So what is Lagrangian subgroup? Well, so for instance, if the TKFT is 3 dimension, like 2+1 dimension, where you can only have particle excitations, then a Lagrangian subgroup corresponds to boson excitation. So you can think of it as this is some kind of isotropic condition with respect to braiding. So I can use the statistics to define like a symbolic pairing the TKFT, and such that if you condense those boson excitations, the theory becomes trivial. So every other non-trivial excitations break non-trivially with at least one of these bosons. So let's call it short topic. So that's the idea. So basically, it's the Lagrangian subgroup is a collection of boson excitations, such that if you condense all of those excitations, you got the trivial TKFT. By trivial, I mean invertible, like SPT. Let's see, I can go to. Okay, so let's see what I'm doing. Okay, so let me just give an example. So let's say we consider like Z2 gauge theory in 2+1 dimension. It can be described by a BF theory with U1 gauge field A and U1 gauge field B with this mixed Chern-Simons coupling. And the theory has Z2 times Z2 particles. So there's electric charge described by the Wilson line of A. And so I'm going to choose Wilson line of A to be my electric charge, while the Wilson line of B is my magnetic charge. Okay. And those particles can in general have braiding due to a Aronoff-Bohm effect. So we can ask, what are the topological boundary conditions? What are the gap boundaries of this TKFT? Well, from field theory point of view, we can impose like Dirichlet boundary condition of A or Dirichlet boundary condition of B. If we impose Dirichlet boundary condition of A, that means that we condense the E particle, well, because the electric charge is described by the Wilson line of A. And if we impose B equal to 0 on the boundary, we are condensing the magnetic charge. So there are two boundaries. And these two boundaries correspond to two different Lagrangian subgroups. So one generated by like the electric charge, the other generated by the magnetic charge. And notice that those two Lagrangian subgroups, like each of them has the property that they are bosons. And if you condense this charge, the theory will become trivial. Okay. That's just an example of what is a Lagrangian subgroup. Okay. So now I'm going to continue with this example to discuss what's the symmetry correspond to this TKFT. Well, for instance, I can consider, so I'm going to talk about 1+1D, symmetry in 1+1D that lives on the boundary of this 2+1D Z2 gauge theory. So the symmetry in 1+1D is the Hsin symmetry. So it has this eta line and this, well, maybe I should use D, this N line, where eta squared to 1. So eta generates the Z2 symmetry, but this N line is the Kromas-Wannier duality that I mentioned earlier. And this bulk TKFT, it can be given by the gauging the Z2, this Z2 spin flipping symmetry in the, that is part of this Hsin symmetry. Now we can ask, why is this Kromas-Wannier duality? Well, it should be used D here. So why is this Kromas-Wannier duality in the bulk? Well, according to a paper by Danfrey and Telemann, it corresponds to electromagnetic duality in the Z2 TKFT that exchange the electric and magnetic charge. So we can think of, so this electromagnetic duality in the TKFT is generated by a Z2 domain wall. And this Kromas-Wannier duality different N lives on the boundary of the domain wall. So domain wall can end on the boundary. The ending locus is this Kromas-Wannier duality. Okay, so let's try to continue with this example. So we want to ask the question about dynamics. Suppose we know there's a 1+1D like quantum system with this Hsin symmetry. Can the quantum system be in like symmetric gap phase? Like for instance, can it be like can it have like finite correlation length? And the method that we are using is asking from the bulk perspective whether this Z2 gauge theory in the bulk has a gap boundary that preserves the symmetry. And the symmetry in this case is the EM duality symmetry. So as I mentioned earlier, there are two types of gap boundaries or topological boundary conditions in Z2 gauge theory. One is the E condensed boundary. Then we have like Dirichlet boundary condition for small a. The other is the M condensed boundary. This is the Dirichlet boundary condition for the field small b. But these two types of boundary are exchanged by the EM duality. So there's absolutely no topological boundary condition that is invariant under the EM duality. Then you can conclude that such Hsin symmetry must, well, it cannot realize in a symmetric gap phase. So whenever a system realizing the Hsin symmetry, either the symmetry must be spontaneous broken, which I'm not talking about this in this talk, or the theory must be godless. Like, yeah.
So if you have a spin manifold, you have you have another boundary condition, which is the ionic one, and that's invariant. So
well, it's a fermion. I mean, you have to talk about fermion condensed boundary, but fermion is not a boson. So
you
yeah.
want to keep the manifold to be able to.
Yeah, but I mean the Z2 K3 is bosonic, so I'm living in a bosonic world.
Okay,
yeah,
good.
Yeah, because
degenerate ground states.
Well, then that would, well, I mean in the bulk of the boundary, in 1+1, yeah, you can have that, but that would like break the symmetry.
No, I think the 4 Hsin fusion category is preserved for that TQFT. And that one I think was constructed in my paper.
Yeah, so for instance, well, I guess the 3 would be like ending locus of the lines in the bulk, something like that. But one of the ending locus will be charged under the symmetry because there's a braiding between the sigma line and the eta line. So at least one of them would be easy to add. Okay, so I see there are many interests. So from now on, I'm going to just generalize the story I told you to higher dimensions. So I'm going to focus on symmetry in 3+1 dimension, described by TKFTs in 4+1 dimension. So TKFTs in 4+1 dimension have been studied by Johnson Free and Matthew Yu. They have some classification. So like this, so a general TKFT in 4+1 dimension can have particles, loops, or membrane excitations. There are like line operators, surface operator, and volume operators. Now in 4+1 dimension, the particles can only be boson or fermion, which is considerably simpler than in 2+1 dimension. Now suppose suppose there are fermion particles. The theory with fermion particles can be obtained from a it can be obtained from a fermionic TKFT, namely TKFTs where the fermions are local particles by gauging the fermion parity symmetry. So I can focus on TKFTs with only boson particles. Now, if all the particles are boson, we can condense the boson. We can condense all the particles. And the end of this condensation will be a TKFT with only loop excitations, because the membrane excitations have to break with at least one particle, and they are confined after we condense the boson. So what are the TKFTs with only loop excitations? Yes. Okay. The claim is that any 4+1D TKFT with only loop excitations, in such TKFTs, the loop must obey a abelian fusion rule. So here's an argument. Suppose we have loop excitation, namely surface operator S and S pung, that obey non-abelian fusion. Namely, suppose if you fuse, well, I guess I use pointer here. If you fuse the surface S and surface operator S pung, suppose you produce a sum of different surfaces Si. Now we can run the shrinking argument. Suppose you shrink the loop excitation to a particle, or you reduce the surface to a loop, on a closed curve. Well, because the theory does not have any non-trivial particle, so you can only reduce to the identity particle. So on the left-hand side, you got 1 times 1, well, that's 1. But on the right-hand side, you got a sum of 1. So that will give you a contradiction unless there's only one surface appearing on the right-hand side of this fusion rule. That means that the loop excitations must obey a abelian fusion rule, namely fusing any 2 loops, it can only produce a unique outer loop. And such TKFT with only loop excitations can be described by a billion two-phone gauge theory. So yeah, U1 two-phone gauge field, which I call capital B, and there can be several of them, and there can be some like transformers like coupling between those two-phone gauge field.
I'm not sure I understand your definitions, because for example, if you take 5D diagram of Witten theory, like this example, and you gauge precisely electromagnetic duality, not all excitation are abelian. You have
so here I'm talking about TKFTs with only loops, no particles, no domain wall, only surface operator. Yeah. So for instance, you can start with a dicointer theory. You condense all the Wilson line, then you got the theory of only loops.
Why?
That's the TKFT I'm talking about. Yeah.
No, I'm not understanding why diagram of Witten theory, in which you say you gauge electromagnetic duality, does not fit in your definition.
It fitting this definition, all right. I mean, take any. What I mean is that take any TKFT in 4+1D. Yeah, lots of operators. They are line operators. They are surface operators. They are like three-dimensional volume operators. There are lots of operators.
Yeah.
Okay. The statement I'm going to make is that suppose you do an operation which is condensing all the lines, you're condensing all the particles. What's the TKFT you are going to get? That's the question I'm addressing right now. Okay. The first thing is that after you're condensing the lines, you're going to TKFT with only surface operator. That's number one. Number two is what's the property of those TKFTs with only surface operator? And the statement here is that such TKFT will be described by a billion two-phone gauge theory. Okay. Is that clear? Yeah. Okay. Another question?
Yeah. So why did the volume operators like the three
Right.
dimensional?
That's by the remote. Right. So here I'm going to assume remote detectability. Yeah. So the membrane, the volume will break with one line, at least one line. Yeah. Everyone is happy? Well, I guess I have to speed up a little bit. Okay. Okay. So let's consider a simple case, like the 4+1D TKFT is a Zn two-phone gauge theory. So let's say example of this billion two-phone gauge theory. So it can be written in this way. I guess we should use the pointer here. So this TKFT. So first thing we can ask, what are the like operators in this TKFT? Well, there are like Wilson lines for this gauge field, two-phone gauge field BE, and there's Wilson line for this two-phone gauge field BN. And they have mutual braiding, like given by the Aharonov bond phase, like given by the nth rule of unity. And importantly, if you compose the electric and magnetic loop, you get the dynamic loop. But this dynamic loop is still a bosonic loop. Just send us the electric loop and magnetic loop. Okay. Now we can ask what are the topological boundary conditions of this simple looking 4+1D TKFT. Well, recall the definition of, well, the topological boundary condition in this billion TKFT should correspond to Lagrangian subgroup. And what is the Lagrangian subgroup? Well, they correspond to excitation such that when we condense the excitation, we get a trivial theory. Okay, so what are the excitations? Well, so first of all, we can sort of do it in backward. So the trivial theory can be described by a two-phone theory, a billion two-phone theory, but the coefficient is 1. And so before and after condensation, the field are related by sort of like change of basis. And so there's a linear transformation between these fields in this trivial theory and the fields in the original theory. So it's by some like integer value 2x2 matrix. Okay. And if you plug in this for a general transformation M, you'll find that this coefficient capital N is just the determinant of this integer 2x2 matrix. And what it means is that so each M specifies a single BF theory, and the matrix M tell you like if you condense some excitations according to the matrix M, you'll get a trivial theory. So matrix M is in one-to-one correspondence with the Lagrangian subgroup. Or in other words, the gap boundaries of the Zn two-fold gauge theory correspond to matrix M such that determinant of M equal to N. And a condensing operator can be read off from this linear transformation. So this B-Plan theory is trivial. So like the image of this M gives you the condensation operator. Now I'm going to impose the symmetric condition. Let's see. Well, okay. I think oh shit. Okay. Okay. Yeah, sure.
Just to the theory that you get is 1 over 2 pi b dBm that you had before, no? When you do the Lagrangian.
Yeah.
Yeah, I mean this one.
Yeah.
Is it trivial only on spin manifolds or also non-spin? Is like
any manifold.
Any manifold.
Here the theories are bosonic. I don't have to impose a construction.
Okay. Yeah.
Okay. So first of all, we should ask what are the symmetries want to talk about. Well, the boundary is a 3+1D theory, and I'm going to focus on the analog of Kerman-Swannian duality symmetry for any 3+1D theory with a Zn one-fold symmetry. And this is the fusion rule. So this capital D is the Kerman-Swannian duality symmetry, and you obey this fusion rule, where eta is a generator of the Zn one-fold symmetry. Then can regard this Kerman-Swannian duality D as defined by like gauging the Zn one-fold symmetry on half space of the domain wall. And the TKFTs are, is given by gauging the Zn one-fold symmetry. In the bulk, you'll produce a like two-fold Zn gauge theory. And again, we can ask the same question: why is this Kerman-Swannian duality D file D in the bulk? We can think of it as the so we can think of it as ending on a bulk domain wall, and this bulk domain wall generates electromagnetic duality in the Zn two-fold gauge theory. So it's like an S transformation on the 2 U1 gauge field. So there are 2 U1 gauge field like B and Bn, and there's a electromagnetic duality symmetry given by the S transformation on the 2 fields. And this Kerman-Swannian duality lives on the boundary of the domain wall that generates the this S transformation. So now we are going to ask, can we find a gap boundary of the Zn two-fold gauge theory such that it preserves this electromagnetic duality symmetry? And the answer is yes. So basically just ask whether this H transformation, so the H transformation is generated by this matrix. You just ask like what kind of like 2x2 integer matrix come in with this H transformation matrix. And you can find there's a general solution given by this. And this corresponds to a gap boundary. And recall that this coefficient capital N in the Zn two-fold gauge theory is related to the determinant of M. So that means that when N equal to like some sum of 2 integers square, in such case, this Kerman-Swannian duality diva can realize in a symmetric gap phase. So in this case, the Zn two-fold gauge theory can have a symmetric gap boundary. And if N is not a sum of 2, like the sum of 2 squares of 2 squares, then it can never be realizing a symmetric gap phase. And now reproduce the result obtained by like some other argument in the literature. But the method generalized to a more general symmetries. So for instance, instead of talking about S transformation, we can talk about like ST, some combination of ST. And again, we can obtain the condition on what kind of duality symmetry with instead of using S, but using like ST to some power, we can can constrain the dynamics when the quantum system has this symmetry. Yeah.
Can you go back to the previous slide?
Okay.
Yes. So I believe when n is equal to 2, no? So Z2.
Yeah.
There is an invariant TQFT on spin manifolds.
Yeah.
Which is
yeah.
like PB.
Yeah,
but there is no invariant TQFT on non-spin manifold.
Yeah.
No? Is it true? So these are, I think these are like, then you're classifying boundaries which exist on spin
Yeah, that's
manifolds.
fine. Yeah.
No, just to know. Okay.
Yeah. I'm just considering like general boundary of this TQFT. Yeah. And these entries are consistent. Well, I mean, can also find the entry in our paper. So we find this method can reproduce known results in the literature. So we are sending our fit. And then we can generalize the discussion to talk about other symmetries, and we can make new prediction. So for instance, the chromatic duality symmetry not correspond to S, but correspond to like ST. If the Z and one function symmetry where with n not equal to those entries, those completed entries, then the presence of some symmetry means that the quantum system must be in symmetric gapless phase. If the symmetry is not broken. Okay. So let's just say, so I would like to call the this existence of symmetric Lagrangian subgroup as kind of first abstraction. And I'm going to talk about second abstraction. So another abstraction is the associator of the symmetry defect. Well, for instance, in 1+1D, there can be F symbol for the duality defect can be like -1 or +1. And in this case, it's usually called from a zero indicator. Now, if we want to generalize to higher dimension, we need to find a way to describe this associator from the point of view of the bulk TKFT. And the answer is that we just stack some SPD phase in the bulk. So let me explain that. So we can think of the symmetry generator as living on the boundary of a bulk domain wall. So like in the case of Kerman-Swannian duality symmetry, they live on the boundary of some bulk Z2 domain wall, like electromagnetic duality defect, or maybe Z4 domain wall. And the associator of this Kerman-Swannian duality symmetry correspond to the associator of this domain wall in the TKFT. And the domain wall in the TKFT, the associator of the domain wall in the TKFT can be described by a SPD phase for the symmetry in the bulk. So that's fine. Okay. So previously I talked about whether the TKFT has a symmetric gap Lagrangian without taking into account non-trivial associator. So if there are non-trivial associator, I have to stack an extra SPD phase in the bulk. Now, we want to ask the question, suppose now we do that. Suppose there's a non-trivial associator. Is that a further abstraction to symmetric gap phase? So basically, it's the same as asking if this extra SPD phase we stack in the bulk have symmetric gap boundaries. Now, if the associator is described by the so-called group cohomology SPD, namely they are given by dipole interaction, then it's known that such group cohomology SPD phase always have a symmetric gap boundary, well, at least for a finite group. The construction is given by this paper by Wang Wen and Witten. However, there are also more general SPD phase called the beyond group cohomology SPD phase. And those SPD phase in general does not have symmetric gap boundary. So I'm going to give an example. So basically the abstraction to symmetric gap phase has two components. So first we have to find symmetric Lagrangian. The second component is to ensure that the associator, the SPD phase correspond to the associator has a symmetric gap boundary. So let me give an example. So let me first mention some property of unitary TKFTs in 3+1 dimension. So the partial function of unitary TKFTs on any manifold such that it can be regarded as the norm of some state must be positive. Like suppose we consider manifold to be K3. And if the associator of the SPD phase it can suppose it produces an anomaly in flow that implies a non-trivial phase in the partial function of the TKFT on K3, then it's in contradiction with this positivity condition and such associator cannot be realized in a TKFT. So for instance, if the associator of some, let's say, Zn symmetry is described by this beyond group homology SPD, so it can be really, well, it's some kind of like global gradient anomaly in 3+ dimension. And so if you evaluate pasta anomaly in flow of this SPD phase, you find out that the partial function on K3 will transform by a non-trivial phase. So in general, you'll find out such beyond group homology SPD phase or the corresponding associator is an abstraction to symmetric gap phase. So there's no symmetric TKFT that can realize the associator. Okay, so let me briefly mention. So far I'm talking about boundary theory as like some theory living on the boundary of a TKFT, but in reality, yeah.
On the previous slide again with the associator, I didn't understand when Konstantin asked about this. So as a monoidal category, it's equivalent to one with a trivial associator. So what does it mean that the associator itself presents an obstruction to something?
Okay, so when I mean associator, it just mean you can fuse the define in different ways, like F symbol. And in higher dimension, there can be, I mean, for instance, in 4 dimension, you can ask, there are different ways of using like 4 domain walls. That will give you some like 10J symbol, for instance. I mean, this. When I say associated, I just mean different ways of using the DFA can produce.
Codimension 1 operators in
codimension 1, yeah,
dimension
codimension 1
higher than 3.
Yeah, codimension 1.
I see. Thank you.
Okay, everyone's happy. I think have to speed up. Okay. So far the theories I'm talking about living on TKFT. So maybe you can ask, like, suppose I'm just talking about ordinary quantum field theory living not on the boundary of the TKFT, but like just purely 3+ D. What should I do? Well, the answer is that I have to choose a polarization, and this has been discussed by many people, like by Frey Telemann, Witten, a lot of people. So the idea is that you have to choose a polarization, which is a topological boundary condition of the TKFT, and so you can put the original theory like on the left-hand side, and this gray region is the TKFT in the bulk, and then you choose another topological boundary condition, which is called polarization. And then because the bulk is a TKFT, you can shrink it. So you collide the 2 boundaries, you got a theory that does not have a bulk TKFT, so let's call it an absolute theorem. So that's basically what you need to do to get a like well-defined, just purely 3+ D theory. You have to choose a polarization, namely some topological boundary condition of the TKFT. Now, if this red boundary is symmetric gap, well, because the blue line is also topological, so you collect, then you got like an absolute theory, which is also symmetric gap. So basically, the discussion I have earlier does not depend on the choice of polarization as long as there is one. Okay. So what do we have so far? So let's talk. I mark the boundary of this like blue region. This is the like a symmetric gap phase, and the white region outside, which is a symmetric gap phase. So what is this boundary? Well, it's symmetric Lagrange and also this associator, or some people call it Frobenius indicator. The next topic, I'll be quick, is about what about this boundary? Like, can we say that because of the symmetry, because of the non-trivial symmetry, the dynamics cannot be non-trivial? What's the criteria that mark this like red boundary? Okay, that's the topic of the second part of my talk. Okay, so well, basically we're asking when is the symmetric gap phase in fact trivial? So non-trivial symmetric graph phase means we have a t-cap. Well, you have t-CAPTs. You have some deconfined topological excitations. Namely, if you have particle antiparticle excitations, you can like nucleate them and then separate them by like very far away and then annul them. Then, in contrast, if the excitations are confined, you cannot separate then arbitrary long distance because of strong attraction or energy cost. And trivial dynamics means that all excitations are confined. There's no excitations long energy or long distance. So how do we know if there are non-trivial excitations in the symmetric graph phase we just talked about? So basically, I'm going to construct a detector for the non-trivial excitations. So how do I construct a detector? Well, so the detector is this green line here. So the red line is the symmetric, is the gap boundary, symmetric gap boundary I constructed, and this blue line is the polarization I choose. Now, suppose there are topological operators that can end on this red line and also end on this blue line. So if the topological operators can end on this red line, well, it belongs to Lagrangian. Namely, there are operators that contained in the t-CAPT. If the operator can end on this blue line, it's also part of the Lagrangian I label this reference topological boundary condition. So I'm going to call this Lagrangian lambda pole for polarization. So the topological operators that can end on both boundary are the intersection of this like Lagrangian for this symmetric gap boundary and the Lagrangian for this polarization. So these are the detector. Now, if the detector is trivial, namely the intersection is trivial, by the remote detector BLT principle, that means that, well, there are no excitation to be a detected. So the excitations that can be detected are the excitation that break with this green line. And after you shrink the bulk part, those like dash line here are the excitations remaining in the absolute theory. Now, if this detector is trivial, that means that there's no excitation to be detected in the absolute theory. So that the absolute theory does not have any non-trivial excitation. Okay. So that's the condition when you have a trivial dynamics in the absolute theory.
So you would have to check all possible polarizations in this case, right?
I just need to choose one polarization. I mean, the polarization specify what kind of absolute theory you want to talk about. So you can choose different polarization to talk about different T+1, T3, but just need one.
I see. So this is, as long as this complement being trivial is true
for one polarization, then I know that there exists an absolute theory that has trivial dynamics, and it has a symmetry. Everyone's happy? No complaints? Okay. Okay. So this situation, well, okay. So this situation is when I do not add addition. Oh, okay. I'll be great. So this situation is when I do not add, when I do not consider like the associator. Now I'm going to consider the secondary abstraction, namely the associator. Okay. So the basic idea is that so what do you need to do when you have non-trivial associator for the symmetry? So first of all, if the associator is trivial, that's the situation I discussed earlier. Namely, you want to check whether there exists a polarization such that it's sort of like monolectic Lagrangian that intersect trivially if the Lagrangian are labeled a symmetric gap boundary. Now, so in such case, it means that the symmetry defect has a well-defined wall volume t-CAPT, because now the bulk is trivial, so there is a well-defined so the symmetry defect is a well-defined like wall volume t-CAPT. And what happens if you turn on non-trivial associator? This is the same as asking whether this wall volume t-CAPT leaving on a defect can realize the anomaly given by the associator. Let me just okay. Well, let me just be quick. Yeah.
But also in higher categories. So at least for 3 categories, it's a known stratification result that you can go from a a non-trivial associator to an equivalent trivial associator. I don't know of such theorems in high dimensions.
Definitely not. I mean, for invertible symmetry, you can have genuine anomaly. Yeah. Let's say you have a 3 category with some like domain walls that generate invertible symmetry. Then
I don't understand.
Okay.
It's a theorem that a generic 3 category is always equivalent to one with trivial associators everywhere for all compositions.
So let me say what I mean. So suppose you find out if you fuse the domain wall corresponding define a different way, you got the like non-trivial isomorphism or non-trivial like maybe differ by a complex number or differ by a phase, then this phase or complex number is meaningful, is physically meaningful. When the corresponding default generates an invertible symmetry, this phase is called is the standard tooth anomaly, like you're doing in QFT textbook.
To me, it sounds a bit like a choice of basis, and that it depends.
It's not a choice. It's not a choice basis. The point of anomaly is that you cannot remove it by remove the anomaly by like adding counter term or like making some redefinition. Okay, but we are talking about different thing, I think. Yeah.
Basis. No, I don't need this. What makes sense to compare different associators in the same tensor category, that you can do. So that's how you can tell that the digraph within twist differs from a trivial digraph within twist.
Right.
But it's not intrinsically a digraph within twist is a non-trivial associator and a trivial one is trivial.
Okay.
You can trivialize both of them.
Yeah.
It's just the natural basis. One of them is trivial, the other is non-trivial, but you're free to choose your basis.
Yeah, okay. So I'm going to fix a basis. Yeah. Okay. Yeah, thanks for the question. Okay. So I think probably need to wrap up soon. So basically, let me just tell you what's the logic here. So the logic here, if there's a non-trivial associator, or when the bulk is TKFT is stuck with non-trivial SPT, is that you can use the decorated domain wall construction of the bulk GSP of the bulk SPT to convert this SPT into a SPT phase on the generator of the symmetry in the bulk. So like in this figure, the symmetry on the boundary is generated by this green line, and it is on the boundary of a domain wall in the bulk that generates the electromagnetic duality. So this is the orange region, and the SPT phase in the bulk is equivalent to having some SPT phase decorating on this orange domain wall. Now this means that, and by anomaly flow, this SPT phase on the domain wall implies that the symmetry default, this green line, must have an anomaly. So whether the case when the bulk has a SPT phase and symmetry can be realized by the trivial dynamics, is the same as asking whether TKFT living on the symmetry default can realize the anomaly on this G domain wall. So, and you can check that in the case of like 1+1D Tambara-Yamagami symmetry, like I briefly mentioned earlier. So you can have a Tambara-Yamagami symmetry with this fusion rule and non-trivial associator or non-trivial F symbol. You can find that you can check that the TKFT on the symmetry default of this D. Well, in this case, the TKFT is actually just a 2-level system, just a qubit. You can check that the qubit can realize the anomaly correspond to the non-trivial associator, and that's why the Tambara-Yamagami, the Z2 times Z2 Yamagami symmetry can be with this non-trivial associator can be realized in a trivial phase, in a phase with trivial dynamics. And you can do the same for like higher dimension. So I'm going to skip that. Okay, so in the high dimension, like for the corresponding duality symmetry in 3+1 dimension, the TKFT is not the qubit system, but instead some like instead the minimal abelian TKFT that Francesco talked about in the morning. So let me skip this. Okay. So in this talk, well, well, I'm sort of quick in the end, but we have marked the boundary between these phases, between these regions of phases using symmetry. So for instance, the distinction between symmetry gap phase and symmetry gap-based phase can be inferred by whether the bulk TKFT have a symmetry Lagrangian and where the proportional indicator forbids a symmetry gap boundary. And we also have marked this boundary, so where there exists a polarization such that intersect trivially with the Lagrangian, this symmetry Lagrangian here, and also where the associator from the which can be regarded as a SPD phase, match the anomaly of the TKFT on the DFA. So that's the main message of the talk. And there are many things to do. So basically the talk, I hope I convey to you that TKFT is a powerful tool to study dynamical constraint imposed by symmetry in quantum systems. So we basically utilize bulk TKFTs to study various dynamical implications from novel and general non-invertible symmetries, which can provide some simpler method for some like results in 1+1 linear literature, and also produce new results in higher dimension. And I want to mention that there's important question for TKFT to understand dynamics of general quantum system, like whether there are gap boundaries or what are the topological operators or what kind of anomalies can be realized in a TKFT. So I'll end here. Sorry for being over time. Thank you.
So based on Yunqing's talk, it seemed like if I also specify a bicharacter, I get further constraints.
Yeah, so
could you
I
say a bit
didn't talk
about
about bicharacter, but that's related to how symmetry acts in the defunct TKFT. So if you want to be precise here, so in the case of Z2 times Z2 times Brownian Yamagami symmetry, I say that the TKFT living on defunct is a 3-qubit system, and this well, where am I? So this symmetry D correspond to a time reversal symmetry on the defunct. So it's a time reversal symmetry in the qubit system, but depends on where you choose the off diagonal or diagonal bicharacter, the symmetry acts in a different way. So well, you can already see the difference of these two bicharacters in the bulk TKFT. So they correspond to different like Z2 permutation symmetry in the bulk TKFT, and this different permutation we're going to be where am I? Well, you will act on this 3-qubit quantum mechanics in a different way. So like one of them, so the 3-qubit quantum mechanics can be developed by like 2 Z2 variables that intercommute. One is like the position, the other is the momentum, and for one bicharacter, the time reversal symmetry exchange the Q and P, the other leave them fixed. And in terms of qubits, one of them has additional Hadamard gate. So K is the complex conjugation. So one of them is just complex conjugate, the other has additional Hadamard gate. And you can check that if you like, because of these different choices, it affects where the qubit system can produce the anomaly. So for one bicharacter, the 3-qubit system cannot produce the anomaly. For the other bicharacter, the qubit can produce the anomaly, correspond to the FS indicator. Yeah.
You also have similar results in 4 dimensions?
Oh yeah. So this is just for one up, but you can do similar things in 4 dimensions. So where the TKFT is no longer a qubit system, is a minimal abelian TKFT, and can show explicitly that in some case the TKFT can reproduce the anomaly. In our case, it does not.
Yeah. For pivotal fusion category, you have an independent definition of Frobenius-Schur indicator. Then you show actually that it only can take the values ±1, and you show that it equals the sign in your F symbol. Is there an independent definition of Frobenius-Schur also for higher categories, or do you just call the sign that appears in certain equations Frobenius-Schur?
So the FS indicator or the associator used in this talk or in the paper can be inferred from the SPT phase in in one dimension higher. So let me maybe I explain that. Just 10 seconds. Where am I? Okay, here am I. Okay, so the usual so let's say we are in 1+1D, and the information indicator are just like the F symbol for the topological defect. Like you can like this configuration can differ by a sign. So one way to understand the sign is to think about it as a number associated to a domain wall in the bulk when they intersect. So you can imagine you play a movie where this configuration slowly moves into this configuration.
Sorry, that's clear to me. So you define Frobenius Schur by design.
Yeah.
What I say is that there is an independent
Oh,
definition.
that's the definition we use. I don't have that. Yeah.
Which is where the name comes from, because it generalizes Frobenius Schur of group representations. And my question is whether something like that, some other definition.
Yeah, that would be interesting to know, but I don't have other definition other than this one using from the bulk perspective. Yeah, thank you. Okay. Okay, thank you.